Hello, I welcome you all in this course on steam and gas power systems. Today we will start with the boiler trial. The boiler trial is the account of, the analysis of the boiler is done and it is account of where from the heat is coming and where the heat is going. It is total balance sheet of heat transmission in a boiler. How much heat is going with the flue gases? In fact, how much heat is going with the burn product? How much heat is going with the air, excess air? How much heat is going with the water vapor? How much heat is lost to the surroundings? It is by difference only. How much heat is supplied to the boiler by burning the fuel? All these are taken into account and a balance sheet is created. So before we go to the boiler trial, we will start with the flue gas analysis. Now, flue gas analysis is very important because with the help of flue gas analysis, you can directly find how much air has been used in burning the fuel. In flue gas analysis, mainly the amount of carbon dioxide, oxygen and carbon monoxide and nitrogen. Nitrogen is by balance, right? 3 flasks are taken. There are 3 flasks. I am just giving the schematic. There are 3 flasks. 1, 2, and 3. They are filled up to a certain level with the liquids. First one is KOH, potassium hydroxide, right? This is to absorb carbon dioxide. Now the second one is having pyrogallic acid, just to absorb oxygen. So the pyrogallic acid absorbs the oxygen, and the third one is having cuprous chloride. Cuprous chloride, and the cuprous chloride consumes the carbon monoxide. So this is for oxygen, pyrogallic acid, carbon monoxide and carbon dioxide. And by balance we get nitrogen. We take fixed amount of flue gases. Let us take a sample of 100 cc of flue gases, and that amount of flue gases is first passed through the KOH, and amount of flue gases, the volume of flue gases absorbed by the QH is noted. Then it goes to this pyrogallic acid tube, and then third one is cuprous chloride tube, and remaining is nitrogen. That is how we get the percentage of CO2, O2, CO and nitrogen. Now with the help of this analysis, we can easily find how much air is used for burning the fuel, right? So for this, we'll prepare a table. Suppose in the flue gas analysis, CO, CO2, N2 and O2, right? The volumetric fraction is X1, X2, X3 and X4. This is volumetric fraction. Suppose 5% is CO, 30% is CO2, 35% or 38 or 40% NO2, 5%, something like that. So they are figures. Now we have taken as variables percentage volume, right? Molecular mass for CO it is 28, for CO2 it is 44, for nitrogen it is 28 again, and for oxygen it is 32, right? Now we will calculate another X, or this is, let us not get confused with X and Y, so we will take Y1, Y2, Y3, Y1, Y2, Y3 and Y4, right? So this is M and X is equal to MV, M and this V, and this will give you 28 Y1, 44 Y2, 28 Y3, 32 Y4. Again, we are working on the same principle. 1 kilomole will occupy a fixed volume, that is 22.4. Right? Now, this is composition ratio in percentage of mass. So, in order to find, this is the composition of gas. It consists 28 Y1 kg of CO, 44 Y2 kg of CO2, 28 Y3 kg of nitrogen, 32 Y4 kg of oxygen. Now again, in order to find percentage here, percentage by mass, we will take sigma Y, right, and 28 Y1 by sigma Y, 44 Y2 by sigma Y, 28 Y3 by sigma Y, and 32 Y4 by sigma Y. Right? So this is percentage by mass. So in exhaust gases per kg, this divided by 100 is kg of carbon monoxide. This divided by this this gives the value of carbon dioxide. Accordingly, nitrogen and oxygen can also be taken. Now here, let us take 1 kg of flue gas. 1 kg of flue gas. 1 kg of flue gas will consist of how much kg of carbon monoxide, that is this one, right, and how much kg of carbon dioxide, this much, right. So carbon per kg of flue gases. Now we have to find carbon per kg of flue gases. The philosophy is, now we will calculate how much carbon is there per kg of flue gases, and per kg of fuel carbon content is there. Suppose carbon content is 0.86 kg, right. So per kg of flue gases, how much carbon is there, and with that we will find how much flue gases is there. What is the mass of the flue gases? So carbon per kg of flue gases is going to be 28 Y1 by sigma Y multiplied by 12 by 28. Naturally 28 will be cancelled out. Similarly, for carbon dioxide it is going to be 44 Y2 by sigma Y multiplied by 12 by 44. This is the amount of carbon available in 1 kg of flue gases, right, and we add these two, then we will get 12 by sigma Y x1 plus Y1 plus Y2, because this 28 and 28 will be cancelled out, 44 and 44 will be cancelled out. So we will be getting 12 by sigma Y, Y1 plus Y2. This is per kg. Suppose there is m kg of flue gases. Mass of the flue gases is m kg. So the carbon is going to be 12 divided by sigma Y, Y1 plus Y2, mass of the gases, flue gases. Now this Y1 and Y2 is, we have taken from volume. Remember, we should not forget, it is from the volume only. Percentage volume of carbon monoxide and percentage volume of carbon dioxide in flue gases, right? That is one thing. Now regarding nitrogen is 28 Y3 by sigma Y. Nitrogen does not take part in combustion. So it was, whatever nitrogen was there in the air, it has come into the flue gases. So kg of air per kg of fuel is 28 Y3 by sigma Y multiplied by mass of the flue gases. Is it clear? This is the percentage of nitrogen in flue gases per kg of flue gases, or per kg of flue gases. This is the nitrogen and it is multiplied by mg here, right? And this further, because we have to find air, so this has to be divided by 0.77, then we will get air only, otherwise it was nitrogen only. So this is the amount of nitrogen. This is nitrogen per mass fraction of nitrogen per kg of flue gases, multiply by mass of the flue gases, divided by 0.77, we will get kg of air per kg of fuel, right? Now from here, the value of mg can be manipulated from this equation to this equation. That will give 28 y3 divided by sigma y multiplied divided 1 by 0.77. mg will be C sigma y divided by 12 y1 plus y2. C multiplied by sigma y divided by 12 y1 plus y2, right? So sigma y and sigma y will be cancelled out, and 28 divided by 0.77 divided by 12. Yes, this is 28 divided by 0.77 divided by 12 is equal to, it is 100 by 33, right? So we will take 100 by 33, y3 divided by y1 plus y2 multiplied by c. It means, now from here, this is kg of air per kg of air per kg of fuel. We are burning 1 kg of coal or fuel. This much of kg of air will be required to burn 1 kg of fuel. That is 100 by 33. Volume of nitrogen in exhaust gases. We have taken some sample. So percentage volume of nitrogen in exhaust gases, percentage volume of carbon monoxide in exhaust gases, percentage volume of carbon dioxide in exhaust gases, and amount of carbon 1 kg of fuel. Or we can write it like this: air is equal to amount of air, and this is N2 percentage of volume, right? So we will write N2 divided by 33 CO2 plus CO and carbon percentage wise, because this 100 will be multiplied to C, it will be per 100. Okay, this is carbon content per kg. So it, suppose it has 86% of the carbon, so C is going to be 86. So this is the formula to find how much air is used for burning the fuel. So directly from this formula we can find how much air is used for burning the fuel. Air may be excess in amount. This is also possible that we supply 20, 30 or 40% excess air, and in the product of combustion carbon dioxide is there and carbon monoxide is also, that is also possible, right? So we will take one numerical to understand this. This numerical states, during the boiler trial following data were obtained. So coal analysis was done, this carbon was 85.5%, hydrogen 4.5%, ash 10%, gross calorific value of a dry coal is 35 megajoules per kg. Moisture, it has moisture 1.8%. Coal consumption is 1450 kg per hour. Boiler room temperature is 25 degrees centigrade. Feed water temperature 55 degrees centigrade. Steam pressure 1.2 megapascal. Steam temperature 250 degrees centigrade. Steam raised 12500 kg per hour. So how much steam is raised per kg of coal we can easily find out. Coal combustion is there, it is given 1450. So how much steam is raised per kg of coal we can find out. Analysis of dry flue gases by volume of gases. This is done by Orset apparatus, as I explained earlier. So in exhaust gases, carbon dioxide is 9.5%, oxygen is 11%, nitrogen is 79.5%, and there is no carbon monoxide. The temperature of gases in the uptake was 300 degrees centigrade mean specific dry gases, mean specific heat of, this is mean specific heat of dry gases is 1.005 kilojoules per kg Kelvin, right. So now we have to prepare complete balance sheet of heat transmission. So first of all, we will find how much coal is spent, or per kg of coal how much steam is raised. So steam raised per kg of coal, steam per kg of coal is equal to 12500 divided by 1450, and that is going to be equal to 8.621 kg per kg coal. So when we are burning 1 kg of coal, this much amount of steam is liberated. Now how much heat is carried by this steam? This we can again look at the Rankine cycle at temperature entropy diagram. The steam here is superheated. So 1, 2, 3, 4, 5. So steam is superheated. So we have to find the value of H1. Feed water temperature will be at H4, and difference of these two will give us the amount of heat transmission to the feed water in boiler. So for superheated steam, we have superheated steam table. At it is saturated, only saturated. Okay, no problem. We have the enthalpy at state 1 H1 from steam table we can take 2783.7 kilojoules per kg. H4 can be calculated from the steam table 230.26 kilojoules per kg, and this heat supplied H1 minus H4 is going to be 8.621 multiplied by 2783.7 minus 230.26, and that is going to be 22013.2 kilojoules per kg. Sorry, kilojoules. Sorry, this is kilojoules. This is kilojoules per kg of coal. Because per kg of coal, this much of steam is liberated. So whatever heating value 1 kg of coal is having, this much of heat is going to the steam. So we can note it down somewhere. So steam is taking away 22013.2 kilojoules. That is per kg of coal. Now air supplied. How much air is supplied for burning the fuel? Earlier we have already done a derivation, and using that derivation, that formula, we can easily find how much air is supplied. So air supplied is volume of nitrogen in volumetric analysis divided by 33, volume of CO2 plus volume of CO, percentage of carbon, right. Now volume of nitrogen, how much volume of nitrogen is there? It is 79.5 divided by 33, volume of CO2 9.5 plus 0 multiplied by carbon 85.5, and this will give us the amount of air supplied, and that is coming 21.68 kg per kg of coal fuel. So 21.68, mass of the air is 21.68 kg. So this is the mass of air which is circulated, but actual mass of air for burning the coal is how much? This is the mass of air supplied, we supplied to the boiler, but how much air has been used? In order to find that, minimum air is equal to for burning carbon we need 8 by 3, right. For burning hydrogen, H minus O by 8 multiplied by 8. For sulfur, 1 kg of sulfur require 1 kg of air. So S, so it is only S. if sulfur is there. Sulfur is there, sulfur is not there. So simply minimum for calculating minimum air. Now this is minimum oxygen, not minimum air. So in order to find minimum air, it has to be divided by 0.23. Then you will get minimum air. This is minimum oxygen. So 1 by 0.23. Now here 0.855 into 8 by 3 plus how much? 0.045 into 8. Oxygen is not there. Oxygen is not there. Okay. And S is also 0. And minimum air is 11.48 kg. So mass of the air supplied is 21.68. So mass of the minimum mass of the air is 11.48 kg. And there is excess air. Now the excess air is equal to this 21.68 minus 11.48 is equal to 10.2 kg per kg of coal. We are just calculating everything per kg of coal, because in balance sheet we have to give in terms of percentage. So if we find all the values for per kg of coal, that will serve the purpose. Now mass of water vapor. Percentage of hydrogen is 4.5%, moisture content is 1.8%. So this moisture is taking heat from the coal, and the liquid is this moisture is converted into vapor, high temperature vapor, and it is going with the flue gases. So moisture is 0.018 plus hydrogen 0.045 into 9. This is the total amount of water present in the flue gases, because moisture is already there 1.8%. So now this plus this will give 0.423 kg of water in per kg of 0.423 kg of water going with the flue gases when we are burning 1 kg of fuel. So mass of the dry air will be difference of this. Mass of the dry air. Dry air will be difference of, yes, this 21.68 minus 0.423 plus coal which is burned, which it is also coming into the flue gases, right? So this is mass of the dry air, and mass of flue gases, dry gases is 21.68 minus 0.423 plus 0.9. Say air which is burned, suppose this is mass of the air 21.68, we can write this way also. Mass of the air is equal to 21.68, mass of the fuel is 0.9. 0.9 is 85.5%, 4.5%. It is 90% to 0.9. So we can add these two, right, and then remove 0.423. So we will get the mass of the dry flue gases. So the mass of the dry flue gases is 22.157 kg, right? So now we have calculated mass of the dry flue gases, mass of the excess air, mass of the air, and minimum mass of air which is required, and excess air also. Mass of the excess air is 10.2 kg, right? So certain amount of air is supplied for burning the fuel, right? So part of the air has been used for burning the fuel. Excess air is this much, 10.2 kg. Air has come to the flue gases. Product of combustions have come to the flue gases. Water vapor has come to the flue gases. Now if you want to have mass of the dry flue gases, in that case we will remove this water content, and in the air we will add mass of the fuel which is coming with the flue gases, because ash will not come with the flue gases. Ash will be settled in the grate itself, in the pit. below the grate. Now, after this is the mass of the flue gases. Now, mass of if we remove the mass of air, excess air, mass of this is mass of dry flue gases. If out of these, if I remove the mass of the excess air, I will be get mass of the combustion products. Flue gases is consisting of the combustion products, excess air and everything. So, mass of the dry flue gases, if I remove excess air, I will be getting mass of the combustion products. So, mass of the combustion products is 22.157 minus 10.2, it is coming 11.95 kg. Now, heat, because this specific heat is given 1.005, here it is equal to the specific heat of the air, sometimes it is different. So, I have taken a generalized case. Here you can take both and both the combustion product and air together, but suppose the specific heat of dry gases is instead of 1.005 it is 1.030. In that case the scenario is going to be different. So, now this is M 11.95, Cp 1.005, delta T is 300 minus 25. So, this is the amount of heat which is going with dry product of the combustion, right, and that is here it is coming out to be 3302.7. we will write somewhere here heat with a dry product is equal to 3302.7 kilojoules per kg. Now, heat in excess air. Now, excess air is 10.2. So, 10.2 into 1.005, 300 minus 25. Here, because Cp is same for both the cases, but again for excess air it is coming excess air it is coming 2819.0 kilojoules per kg. Now, vapors. We have vapors also. The mass of the vapor is 0.423, right? And the enthalpy of the vapor is also changed. It is enthalpy at 300. It is 300 outgoing 300 degrees centigrade. So, enthalpy of water at atmospheric pressure at water is at atmospheric temperature is 25, enthalpy of 300 and minus enthalpy at 25. So, it is coming around 3074.5 minus 104.83 and it is 1256.2 kilojoules per kg. So, now we have everything. Now, we have information about how much heat is going with the, first of all let us see how much heat is supplied in the boiler. Heat by coal. Heat by coal is equal to 35,000 kilojoules per kg, that is 100% heat, right. Now, steam, where it is going? It is going into the steam 22013.2 kilojoules, it is kilojoules, right, per kg, right, and it is coming 62.9%. So, 62.9%, that is efficiency of the boiler also, 62.9%. Now, heat in dry product is 3302.7, it is 9.4%. Heat in vapor, just now we calculated 1256.2 and that is 3.6%. Heat in excess air, that is also heat in excess air. Heat in excess air is 2819, and that is 8.1%, and that is coming around 84.0%. Right? Now this is 100%. So 16% of heat is unaccounted. So 16% of the heat is going to the surroundings in the form of radiations, right, in the form of conduction and in other forms. So that is how the boiler trial is taken and the balance sheet of boiler is prepared. From the next class, we will start with the nozzles.